The next part of the lecture I want to discuss first a general technique that's used for much more than just trees, decision trees, and then this technique, which is called the Bootstrap, I'm going to apply to the decision tree problem. First, let's discuss the Bootstrap in the abstract. So this is a very important statistical technique. It's very general. And we're going to see how it can be used to learn something called ensemble classifiers. The Bootstrap is essentially where we resample from our data. And we use these resampled data sets to improve some sort of an estimator. And what we're going to see when we construct these ensemble classifiers is we are going to generate many mediocre classifiers. So we're going to get models that are, each individual one is going to be not so great. However, when we put them together using a technique called bagging, their combination suddenly makes the overall classification much better. So first let's go through the Bootstrap in general. What we have as input is a set of data, x1 through xn, and also an estimation rule, S hat, of a particular statistic, S, that we're interested in. So for example, our data set could be x1 through xn, and we might be interested in learning the median of the true underlying distribution that generated this data. So we don't care about the median of the actual data that we have. We want the median of whatever distribution generated this data that we don't get to see. Of course, because we don't have an infinite number of samples from the underlying distribution, we can't find out what exactly is the median. So what we do is we have an estimator S hat, which estimates the true underlying median to be the median of our data set. All right, so this is the setting that we're in. This motivates something called the Bootstrap algorithm, and so I'm first going to discuss it in the abstract. First, what we do is generate a set of Bootstrap samples. So we're going to call these B1 through B capital B. So we have capital B different Bootstrap samples. For each individual sample, we construct this set by picking points from our data set randomly n times with replacement. So we have n points in our data set. For each sample, little b, we construct a brand new data set, also of size n, which we construct by sampling n times from our original data set uniformly at random with replacement. So each particular point xi can appear in this set multiple times. So in this sense, each one of these sets is only going to contain data from our original data set. However, each set is going to have each individual observation duplicated a certain number of times or not contain particular observations. So a particular xi might not appear in a particular sampled data set. So each of these Bootstrap data sets is like a view of our underlying of the original data set. And then when we want to calculate our statistic, we simply calculate it using the bootstrapped set. So for example, for the median, we calculate the median of the bootstrapped data set. And then we estimate the mean and the variance of our statistic by averaging over our bootstrapped calculations of the statistic and then calculating the empirical variance, which gives us some uncertainty. So the power of this idea can be seen in the example of estimating the median of a data set. So imagine that we have n observations where each is in R, so n one-dimensional values. And then we want to find the median, estimate the median of the distribution that generated this data set. The way that we do this is we simply sort these x1, these values in ascending order, and then we pick the middle one, or if there's an even number of data points, we pick the average between the two middle ones. And then that's our estimate of the median of the underlying distribution that generated this data set. So the issue is, how confident can we be in that estimation? Well, if we want to know how confident we should be in our prediction of the median, we would have to find the variance of that median. But how can we do this? We only get, for a particular data set, it seems like we only get one possible value for the prediction of the median. How can we get multiple values, or how can we somehow evaluate our uncertainty about that prediction? So that's where bootstrapping comes in. What we do is we generate capital B different bootstrap data sets. For example, for B1, we simply pick n times from a distribution uniformly on our data. So again, some of these are going to repeat, and some of them are not even going to appear in B1, and we do it randomly. We then calculate the median of each individual bootstrap data set. And so we get capital B different estimates of the median. We then say that our expected median, the median that we're going to predict, has an expectation of the average of the median of each individual bootstrap data set, and our variance or uncertainty about that prediction is the empirical variance of the medians that we get from each of these individual data sets. So that's a way to gauge our uncertainty about our prediction of the true underlying median. It's remarkably simple, but there's quite a bit of theory underlying this technique that that relates this simple technique to something that's actually theoretically correct.